Alright, so in this lesson we're going to start looking at electric potential energy and kind of talk about what that means and do some problems with electric potential energy. The thing to point about the electrical force as defined by Coulomb's law, the F equals 1 over 4 pi epsilon naught Q1 Q2 divided by R squared, is that happens to be a conservative force. Remember back to when we talked about forces and whether or not a force was conservative, there are really two definitions that make a force a conservative force. The first of those definitions is the work done by that force if the starting and ending locations are the same as zero. Gravity is a good example of another conservative force. The second definition is that the work done by a force is path independent, meaning as long as I went from point A to point B, it doesn't really matter what path I took to get there. The only thing that matters is I went from point A to point B. So we can actually define potential energy both in terms of two charges, 1 over 4 pi epsilon naught Q1 Q2 over R, and you can actually prove this is true by looking at force. Remember that force is the derivative of this thing, and that our force is negative the derivative of potential energy, which that would work. If we had a system of charges, what we'd have to do is do Q1, Q2 over R for each charge and just add up all those terms. And so here would be a system of 3 charges. If we had a fourth charge, we'd have to have Q1, Q4, Q2, Q4, and Q3, Q4. So you'd have 3 more terms. 5 charges would be another 4 terms. So you can see this can get fairly long if you have a large system of charges. So let's find the potential energy of a system of 3 charged particles that are put at the corners of an equilateral triangle with sides of 15 centimeters in length, and the charge Q is defined as 150 nanocoulombs, and charge Q1 I said is plus Q, charge Q2 I said is negative 4Q, and charge Q3 is plus 2Q. So we're really going to use this formula here. The thing to remember is that we need to do some unit conversions. We want charges in coulombs. Nano is times 10 to the negative 9th. Centimeters, we want that into meters, so that'd be 0.15 meters. So 150 nanocoulombs would be the same as 150 times 10 to the negative 9th, or 1.5 times 10 to the negative 7th. So there's Q1, there's Q2, 4 times 150 is 600. There's Q1, there's Q3, 2 times 150 is 300, and there's Q2 and Q3. And because this is an equilateral triangle, that 0.15 meters is the same for all. So if you plug all that into your calculator, what you end up with is negative 0.0135 joules, or about negative 14 millijoules. Milli times 10 to the negative third, there'd be your decimal point. Multiply this by 1,000. So some things to not be too concerned about. Remember that potential energy can be negative. The thing with electrical potential energy is we generally define it as zero potential energy at an infinite distance. If 2 charges are infinitely far apart, they have zero potential energy. So this just happens to be the fact that there's this negative charge in there that is fairly large compared to the other charges. Don't get too concerned about a negative potential energy. That kind of does happen. It just means you're at some potential energy lower than what this would be if these 3 charges were infinitely far apart. The second type of problem that we can do using electrical potential energy is one that deals with the conservation of energy. And we're going to have a positively charged particle with a mass of 3 times 10 to the negative 6th kilograms and a charge of plus 3 microcoulombs. Micro, remember, is times 10 to the negative 6th. And it's going to be shot toward another stationary charged particle of 6 microcoulombs. We're going to assume that this stationary charged particle is not only stationary, but it's fixed. It can't move, or it's so large that it's not going to move in comparison to this particle. The 3 microcoulomb particle is initially at a distance of 0.25 meters from the other particle and is moving at a speed of 1,000 meters per second. And I want to know how close do the 2 particles get. How close does this particle get to the other particle before it can't get any closer? So what's going to happen is this particle is moving toward, as the 2 positively charged particles are moving toward one another, is there'll be a repulsive force. So this particle will be slowing down, and at some point it's going to come to 0 meters per second. After that point, what's going to happen is the particle is going to fly away because of that repulsive force. So we want to figure out when does the smaller of these 2 particles come to a rest. So let's use conservation of energy. Potential energy plus kinetic energy equals potential energy plus kinetic energy. Well, we can plug in things about our potential energies. It's Q1, Q2 times R0, which is 0.25 meters. And I have 1/2 m V initial squared. I know V initial is 1,000. And I know K final I'm going to define as 0. I'm looking for when does this particle get to 0 meters per second. And so really I'm solving for this R final. So I can actually calculate out these two energies. I know I normally don't do it that way, but what you get is you initially have 0.648 joules of potential energy and 1.5 joules of kinetic energy. So those add up to be 2.148 joules. I've multiplied RF to the other side so I can substitute and solve for it. And so if I solve for it, what I get is that these two particles, the closest they'll ever get is 7.5 centimeters, or 0.075 meters. So that kind of does a quick overview of a couple of different problems you can use electrical potential energy for. It could just be plugged into a conservation of energy equation like gravitational or spring potential energy. In fact, you can maybe envision a problem where all three are true. Maybe I'll do the Millikan oil drop experiment where you have electrical potential energy and gravitational potential energy kind of playing with each other a little bit. That's an interesting problem to look at. So that's a quick overview of electrical potential energy. What we'll start to look at in the next lesson is the term electric potential.